The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, hi everyone, my name is Matt Smith, and I'm part of a group along with Wonjoon, Ryan, and Qunya, and we did a project where we were using ZMAX to design a Cooke Triplet. The Cooke Triplet was actually first designed in the end of the 1800s, and here's a picture on the right there from the original patent that was designed, back in the day. But first we'll talk about what Cooke Triplet is, a little bit about ZMAX, a bit about the aberrations that it corrects, then we'll present some of our results from the optimizations that we ran.
The Cooke triplet is composed of a negative flint between two positive crowns. Crowns have higher V values, also known as the reciprocal dispersion compared to the flints. The Cooke triplet is famous for containing the smallest number of elements that can correct all seven-sided aberrations, and the design principles used include choice of lens power such that their sum is approximately 0, the use of space positive and negative lenses, and the use of approximate front-to-back symmetry. So now we give a quick review on the monochromatic sided aberrations that we aim to minimize in our design. The spherical aberration occurs due to increased refraction of rays further away from the optical axis. Astigmatism occurs when the tangential and sagittal images do not coincide. Coma is defined as the variation of magnification with aperture. Field curvature occurs when the field curvature is the longitudinal departure of focal surfaces from the ideal image surface, and distortion occurs when the image of an off-axis point forms further or closer to the optical axis compared to the image height given by approximation.
So basically, for our design, we chose to use 3 simple lenses since it was basically trying to make it the least expensive thing to manufacture, and also cuts down a lot of the difficulty with alignment. The original patent used compound lenses, which gave them much more adjustability, but it also made it so that the system was very difficult to assemble and align correctly. So we had a total of 14 variables, but essentially. There's the six curvatures, 2 for each lenses, 3 lens thicknesses, 2 air gaps, and 3 glass choices, which we could all vary to try and control the aberrations in the system. And so our first design is this one. Right here? It was optimized to focus objects at infinity to an image plane 60 millimeters behind the rear of the lens. And for comparison, we also designed the same system with using a single lens, which, not surprisingly, has a much harder time focusing the light because it has much less control over the aberrations. These spot diagrams basically give an idea of what rays of light coming in from different angles from infinity are focused by the system. And you can see for both these are on the same scale. About the bar represents 1 millimeter. So you can see here that the single lens shows significantly poorer focusing, and also at higher angles of high degree of coma coming in, which is very detrimental to the image, the ability to focus any light. And compared to the Cooke triplet, instead of the spots being about 1 millimeter in radius, they vary between about 40 to 100 microns, so significantly better focusing and also much less coma. At higher angles, there is some astigmatism coming in, which is hard to see on this diagram, but we can show you a more detailed one later. And to give you an overview of the chromatic aberrations, we compared the focal shift for different wavelengths for on-axis light. These ones, basically, they're zeroed around the green axis. And the primary difference between the 2 graphs here is the scale. This one varies from 0 to about 100 microns, while the single lens actually varies from about 0 to 1,500 microns. So overall, the Cooke triplet reduces most of the aberrations here by about an order of magnitude. And we also next we compared the field curvature and distortion. These graphs both have the Cooke triplet and the single lens plotted on the same graphs to give you an idea of their relative magnitudes. And essentially, compared to a single lens, the Cooke triplet image looks essentially flat, with basically the maximum variation in the field curvature is about 50 microns. Meanwhile, this one, absolute variation is largely dependent on the height of the rays entering the angle of the rays entering the lens, and varies by several millimeters. And here and the distortion also is much worse for a single lens. The Cooke triplet actually is able to minimize distortion until about 15 degrees. The rays become more than 15 degrees off axis. And essentially, the original design parameters that Taylor came up with was to try and have some of the powers of the lenses be about equal to 0, which effectively minimizes field curvature and distortion. And then the other, we use the lens curvatures and materials to try and basically take care of the other Seidel aberrations, coma, chromatic aberrations, spherical aberrations. And the last graphs we have for this set of lenses is the modulation transfer function, which gives you an idea of how well they perform relative to the diffraction limit. So in this case, aberrations essentially serve as a phase modulation on modulate the phase of the transfer function. So that they'll always be less than or equal to 1, so they can never increase it. They can only decrease the lens performance below the diffraction limit. As you can see, for the single lens, basically it drops down very rapidly to 0 here, which greatly limits the amount of spatial frequencies the lens can focus. But the Cooke triplet, while it does operate significantly below the diffraction limit still, can capture much higher spatial frequencies and focus them, which resulted in the much sharper spot diagrams we saw in the previous slide.
Next, we explored the optimization with different image distances between the lens system and some image plane. First of all, the system had been optimized with the 100 millimeter image distance, and next the thickness of lens and curvature of lens and space between each lens were optimized with the 50 millimeter and 30 millimeter image distances. In this case, we fixed the types of glasses and we only used 11 variables. Although the short image distance requires some thicker glasses for both positive lens, this first positive lens was very sensitive for this optimization process. On the contrary, the space between this negative lens and second positive lens was changed from 6.6 millimeter to 8.1 millimeter. About the aberration, we can see the increase of the most aberration with the decrease of the image distances. If we compare it with some single lens cases, we can see the most aberration decreased 1 or 2 order of magnitude. It means that the Cooke triplet is very robust system, and this point is very positive for camera or some projection system that are used in some various image distance. Also, we made more constraints to control the design parameters. 3 glass thickness constraints were added as the initial condition. In this case, the initial glass thickness was fixed as some optimized value for 100 millimeter image distance, and we can evaluate the robustness in this Cooke triplet system. First of all, the space between the negative lens and second positive lens expanded from 13 millimeter to 15.5 millimeter. And next, the space between first positive lens and negative lens was decreased from 5.2 millimeter to 2.5 millimeter. this means that in spite of the decrease of image distance, this Cooke Triplet requires a similar large space to optimize this system. Also, the most operations were magnified in comparison with this previous free glass thickness cases, but it is still better than some single lens case.
Next, we optimize the glasses used in a Cooke Triplet pattern. As seen here, for glass optimization, we only vary the glass and we keep the spaces between the lenses and the object and image distance constant with minimum changes to the curvatures. After optimization in Zmax, the glasses change such that the negative element has the same refractive index and higher dispersion, while the positive element has a higher refractive index and higher dispersion compared to the original glasses. We can see that there's a significant increase in the refractive index difference between the crown and the flint in the optimized design. So here are the outputs for comparing the pattern and the optimized design. We can see that the optimized designs gives better images, and from the field curvature and the distortion plots, we can see there's reduction in field curvature and distortion. From the spot diagram, you can see that there's reduction in astigmatism and chroma. And then from the plot below, we can see that the optimized design gives a shorter range of focal shift, which imply a reduction in chromatic aberration.
Try that. So once you have your optimal design, it's important to understand like how kind of what the previous group did, understand how much you can vary your alignments and your thicknesses from a manufacturing sense, and see how that influences where you are in the optimum. So what we did here was took the first plot that Ryan showed, the full optimization. We had 14 design variables, and what we did is went through and perturbed each surface slightly. So we perturbed each surface between plus minus 1 millimeter. So on these plots, this plot is for the first surface here. This plot is for the sixth surface here. And the horizontal axis is the change from the optimal design point. So 0 means you're at the optimal radius of curvature for that surface. And then as you subtract off millimeters or add millimeters, that's perturbing around that optimal point. The vertical axis is the Seidel coefficient for a given Seidel aberration. And the Seidel coefficient is measured in waves, and it's an indication of how much aberration, how much of a particular aberration you have present in your wavefront. And one thing to notice comparing the first surface and the last surface is that the first lens is highly curved compared to the last surface. So the optimal value for the first surface is about 26 millimeters. For the last surface, it's negative 43 millimeters. So the first lens is relatively highly curved, which means that its contribution to distortion is much more pronounced. So this pink line is distortion, and you can see it's the slope is much greater here compared to the last surface. So, and that actually applies to the other aberrations too. That changing the curvature on the first surface, the first surface is like really sensitive to changes in curvature. So what's happening basically is the first surface is doing most of the work, bending light and doing the imaging. So the downstream lenses are essentially correcting for the aberrations introduced by the first imaging lens. If you look at the root mean square of these aberrations, which is what Zmax is trying to minimize, you notice that for the first surface, there is kind of a little local minimum here, whereas for the last surface, there actually is no local minimum on this plot. And that's actually true for all the surfaces besides the first. And the reason for that is because the first surface is most sensitive to changes, and it bends light the most. So Zmax is going to try to get that first surface to a minimum. If that first surface wasn't at a minimum, then it wouldn't matter what you did downstream from there, because this dominates the aberrations that you're introducing. We did the same thing, tolerancing the spaces between the lenses. So what you see is that the second space, the distance between the second lens and the third lens, is much more sensitive than the first space, particularly when it comes to distortion. Also notice that field curvature is constant for the spaces, for tolerancing the spaces, and that's because field curvature isn't dependent on the position of the lens, only on the power of the lens, because that's what field curvature is, a change in the focusing point as you go off axis, and that's not going to be changed by the relative spacing of the lenses. So just a few conclusions here. Basically what I said before is that the first lens of the Cooke triplet is what dominates the aberration because it sort of does most of the work for imaging. So if you were to make the first lens some sort of more complicated aspheric element that had fewer side-L aberrations to begin with, your performance would greatly increase because the downstream lenses wouldn't have to correct as much from the get-go. All the design variables, those 14 design variables, are highly interdependent, so it makes the optimization a challenge. So when you change one, if you change one radius of curvature, you don't just get one side-L aberration changing, you get all of them changing in kind of coupled ways. So it's a highly coupled problem, and we had to run on the order of 1 billion iterations for sort of our big optimization in order to converge on a solution. But in general, the Cooke triplet does do a good job of reducing the side-L aberrations for maintaining a relatively large aperture relative to its focal length. And I guess for its time, it was, I guess, the fastest lens that was available. And so even though it was designed over 100 years ago, it still remains a relatively optimal design, I guess. So here are references, and we'd be happy to take questions.
Questions? Maybe I'll start. Yeah, go ahead.
What optimization algorithm did you use? So 2 questions. One, what optimization did you use, and how did you decide to define your merit function?
For the optimization, we essentially asked it to, it was primarily minimizing the side-L aberrations on the image plane, and then we also set it to basically set reasonable constraints on the lens parameters to make sure, like, keep the thickness below 20 millimeters. Set a range on the acceptable radius, and so on. And then essentially the rest of the things we made variables. This image shows basically the Zmax user interface. And so here's where we define the merit function, which solves for the coma, primary aberrations, then sets constraints on the lens parameters. And here's where we defined the initial values and also what we wanted to use as a variable in each simulation. So this one's set to vary all the curvatures, all the distances, and the glass types, which results in, like, theoretically, if you want to test 10 things for each one, that's 10 to the 14th variables. But Zmax is good at sifting through that to reduce the number of tests you have to do to find the optimum. In this case, it ran about 10 to the 10. Any other questions?
You mentioned that the higher the flint, the better the chromatic aberration capability. Is it a same intuition? For example, you mentioned, I think you explained very well why the curvature of the first lens is very important for the correction, right? Mm-hmm. Is there a similar explanation for why the flint is important?
We're not. The essential idea is that since the 2 positive lenses are doing the primary amount of the imaging, we wanted to keep the dispersion low there, and then the third, the negative lens was like less critical. I don't know, Qunya, did you find a reason why that varied? Yeah.
I think I only vary the refractive index and the dispersion, so. You're referring to the height of the flint?
Yeah.
We actually kept the, sort of like the shape basically the same. It's only the refractive index and the dispersion that changes. So I'm not sure about how the height of the flint will actually affect the design.
Well, in this case, the size of the negative lens actually sets the aperture for the system instead of actually using diaphragm stops, which is what the cameras at the time had to rely on to minimize aberrations, which severely limited the amount of light they could collect. So in this case, this, what is it? The size of the negative Flint element essentially sets how much light the rest of the system can collect, and the other the two positive lenses were scaled relative to it.
Any questions from Singapore? Singapore is very quiet. Is it because you guys had to be temperature tested before you came to class, or? You guys here don't know, but in Singapore they're very worried about swine flu. So there is a military guard in front of each building, and they actually take the temperature with. You guys have IR viewers, I think, or something, right?
Yeah, he has a thermometer. Yeah, he has a thermometer here.
And every day they have to email, at least the staff in the research center where I work, we have to email our temperature every day and fill out a form. Yeah, it's very interesting.
Yeah, I had a question. You mentioned that the shadal aberrations are coupled. So if you defined a pupil for your system and use Zernica polynomials, would you be able to uncouple the aberrations and I mean, the Zernica polynomials are orthogonal basis for wavefront in the pupil plane. So does Zemax do that?
Yeah, so Zemax does tell you what the Zernicke polynomials are. It'll decompose your wavefront into Zernicke polynomials for you. What I was referring to was the fact that the Seidel coefficients are coupled in the sense that if you change one variable, more than one Seidel aberration is affected. And because the Seidel aberrations can be mapped onto Zernickes, the same thing would apply. So changing one variable would also change some linear combination of Zernickes rather than just one Zernicke. So it would still be coupled, even though you're representing the aberrations in an orthogonal way. Anyone else?
Okay, thank you.